Today I'm going to talk about testing properties of multiple distributions with few samples. This is a joint work with Sandeep Silva. In learning theory, it is very typical to model the data points in a data set as IID sample from some unknown distribution. The question is this model really compatible with the way that we collect data in the real world? Consider the following example. Suppose we have an online shop and we have a data set of the items that is purchased in this shop. In the previous model that I mentioned, we can view each of these items as a random sample from some unknown distribution. However, the way that this data set is actually generated is as follows. There are several customers. Each customer has made a few purchases, and there is no reason to assume that two different customers are choosing the items according to the same distribution. So essentially, we need a model that led us to assume that the data points are coming from multiple sources or potentially different, and also each source may only provide a few samples for us. Another example is the medical record. Suppose we have several patients and we have the medical record of these patients. One thing to note is that we need an agreement among our sources to be able to draw any meaningful conclusion. For example, if we look at the blood pressure of different patients with very different disease, we may not be able to make any inference about the distribution over the blood pressure. So we need some sort of an agreement assumption. Our main goal here is to provide a new model which addresses the aforementioned issues, and we solve a few distribution testing problem in this new model. Let me first define the standard model of property testing of distributions, and then I will mention a new proposed model. In distribution testing, our goal is to distinguish the following cases. We want to distinguish the case of where the distribution has a property, or it is in a set pi, or it is epsilon from having the property, meaning that it is epsilon from every distribution in pi for some notion of distance. The distance that we consider in this talk is the L1 distance, or equivalently the total variation distance. Several problems have been studied before in this framework, like estimating the support size, testing whether a distribution is uniform, testing the shape of a distribution, and other problems. In this framework, in the standard setting, we have some unknown distribution Q. We assume it's a discrete distribution over 1 to n. We receive IID samples from that distribution, and the tester, upon receiving these samples, is supposed to distinguish the following cases with high probability, let's say 90% of the time. The first case is where Q has the property, or it is in the set pi. And the second case is when Q is epsilon far from having the property is epsilon far from pi. The goal is in this setting is to use as few samples as possible and obtain the optimal sample complexity. Now we propose a new framework for testing problems. In this framework, instead of having a single underlying distribution, we have S distribution denoted by P1 through PS. Each of them provide one sample. In some of our problems, we actually require to have one sample in expectation per distribution, and the distribution wants to distinguish the following cases. In the first case, all the PIs have the property, or they are in the set pi. And in the second case, all the distributions are absolutely far from having the property. Here, our goal, and instead of having the optimal number of samples, is actually having the optimal number of resources, having the optimal number of sources, which is equivalent because each source, which is equivalent to the case that we are obtaining the optimal number of samples because each source provides only O of 1 samples. The specific problem that we consider is the following. For some distribution Q, we want to distinguish the case whether all the PIs are equal to the Q or all of them are at least epsilon far from Q. We consider three different cases for Q. The first one is when Q is uniform. The second one when Q is available explicitly to us, so we know the probability of every single element according to Q. And the last one is the case where Q is only available via samples. The standard versions of this problem, where we have only one distribution, have been considered in the literature before, and they're called uniformity testing, identity testing, and closeness testing. As I mentioned earlier, there should be some agreement among the sources. Now I want to talk about this agreement assumption. First of all, let me explain that it is impossible to solve this problem if there is no agreement assumption. Consider the case where Q is uniform, and consider the following two cases. In the first case, all the PIs are uniform, and in the second case, each PI is a singleton distribution over a random element, meaning that the PI assigns probability 1 to a random element. Clearly, the first case, because all the PIs are equal to a uniform distribution, are equal to Q, the first case should be accepted. On the other hand, in the second case, all the PIs are very different, are very far from being uniform, so the second case should be rejected. So any testing algorithm should distinguish these two cases. However, since the singleton distributions are over a random domain elements, what we eventually see from these two cases, if we draw one sample per distribution, we would only see a set of samples drawn uniformly from 1 to n. So these two very different cases may actually give us a very similar output, and they are in fact indistinguishable. So we need some sort of an agreement assumption here. What actually happens here is that one distribution is assigning very high probability to a domain element, while the rest of the distributions are assigning probability 0 here. So in some sense, the probability that we will end up assigning to a single element is sort of uniform at the end, and the effect of these discrepancies are cancelled out at the end. So the agreement assumption that we propose is essentially something to prevent such cancellation. So we assume that there are two subsets of the domain. So we can partition the domain into two sets, A and B, such that for the set A, every distribution Pi should assign a value to the elements in A such that should assign the probability to the elements in A, which are higher than the probability that Q assigns to them. And for B, the probability of Pi should be lower than what Q is assigning to them. So for example, here we can have P1 and P2, and as you see on A, the PIs are higher, and on B, the PIs are lower than Q. I want to mention that this assumption is actually weaker than assuming that the PIs are the same. So assuming that each sample is drawn from a single distribution P, where it means that P1 through PS are all equal. isn't a stronger assumption. So it means that any result that we derive in our model is essentially stronger than what we would derive in the standard model. Let me talk about our results. So for the three cases I mentioned, we assume, for the first case, we assume we have exactly one sample per source PI, and for the rest, we assume that there are Poisson of one sample. When we are assuming that there are Poisson of one sample, it means that in the worst case, we are only requiring log n samples for a few distributions, and in expectation, we only require one sample per distribution. And we have the following sample complexity. Since our model, as I mentioned, is requiring weaker assumption, the lower bounds and the standard model directly apply to our model. So we can use the lower bounds in the standard model, and it turns out that our sample complexities are optimal. So for the rest of the talk, I will explain a few high-level idea of the proof for the uniform case. So suppose Q is a uniform distribution. Even in the standard model, the way that we solve the uniformity testing is by looking at the repetition in the sample set. So if we have a sample set that contains many repeated samples, we essentially draw this conclusion that the underlying distribution is non-uniform. The way that we quantify the repetition is that we count the number of pairs of the samples that are equal. So for example, in the following sample set, we have 4 pairs consist of equal samples. So if all the PIs are uniform, it is not hard to see that the probability that the ith and the jth sample are equal is exactly equal to 1 over n, which implies that in expectation, the number of collisions that we have is to choose the number of samples divided by n. And for the case where we have the PIs, for the case where the PIs are equal to some distribution P, where P is absolutely far from being uniform, this probability is essentially a bit higher than what we expected in the uniform case. So it is higher by a factor of 1 plus epsilon squared, and this is usually enough for us to distinguish the cases. However, since we are assuming multiple source framework, we cannot really use this second part, and we may not be able to assume that this number is high. So the main issue is that we may actually, if we have two distributions, let's say PI and PJ, such that the parts that the PIs are far from uniform are not overlapping with each other, so they assign the probability other than 1 over n to different subsets of the element. It turns out the probability that the I sample and the J samples collide with each other is exactly 1 over n. This quantity is exactly what we would expect to see if the underlying distributions were uniform. This is bad for us because this case should be very far from uniform, so we want to be able to see a different behavior from these two distributions, and having the same probability for collision essentially doesn't help us. So although that in this case the collision probability is the same for PI, the collision probability between PI and PJ is the same as the uniform distribution, we will be able to show that it is not possible to come up with a set of disjoints a set of disjoint subsets of the domain if we have too many sources. So if we have square root 10 divided by epsilon square sample, we will start seeing higher rates of collisions. And at the end, we will be able to also analyze the variance of the number of collisions in this case, even though that the underlying distribution is not the same, and show that we can actually distinguish the affirmation cases. Thank you.